Hey guys, Dr. Cadell here, and this is the density experiment. So there are two parts to this experiment. In the first part, you're going to measure the mass of a measured 10.00 milliliters of deionized water 5 times. That will allow you to calculate the density, because we know that density is mass over volume. You'll measure the mass 5 different times, and you'll see it's not going to be exactly the same each time. The volume each time, though, will be 10.00 milliliters, because we will use a volumetric pipette. Those are the only measurements to make for the first part. It's really simple. But what you're going to do with those measurements is you're going to determine how accurate and how precise you are. Remember, accuracy is measured by percent error. So there's a table in your lab that gives you the true value for the density of water at different temperatures, because remember, density changes with temperature. So I'll show you how to do this, but you look up the density of water at whatever the temperature of your water is. That'll be your true value. The average density that you get from your measurements will be the experimental value. So the percent error is just your experimental value minus the true value, which you look up, divided by the true value times the 100. Remember, guys, the 100 is exact. And the smaller the percent error is, the more accurate you were. The other thing you're going to do with your numbers is you're going to find how precise you were with your measurements. And that, remember, is measured by the standard deviation, which is that equation right up here. So remember, the sigma stands for standard deviation, and the formula is just the square root of the sum of the difference between each value and the average value. Squared, add them up, divide by the number of measurements, which for you will be 5. That gives you the standard deviation. The smaller that is, the more precise you were. Now remember, so this is what each of these things are in this equation. What you're going to report at the end, in your conclusion, is you're going to give me the density of water from your measurements, which is going to be your average, plus or minus whatever your standard deviation was. So, 0.9983 plus or minus 0.002 grams per milliliter. So, I just made those numbers up, but that's how you're going to do it. Now, when you calculate your standard deviation, we only care about the first 1, or maybe 2. Yeah, really just the first 1 non-zero digit. And so that's the first part. Really simple, right? And we'll do this in a minute. So for the second part of the experiment, you're going to take some measurements that will allow you to determine the composition of the brass that makes up a cylinder. So a brass cylinder is made up of, brass is made up usually of copper and zinc. You're going to determine what percent of this brass is copper and what percent is zinc. Different kinds of brass have different compositions. The way you're going to do that is it ends up that if you measure the density of your cylinder, and knowing the density of pure copper and pure zinc, you're able to calculate the composition, and I'll show you how that works. So if we come over here and look at these equations, the density of a mixture is equal to the fraction of each component times the density of that component. Now, this is an important concept. This is called a weighted average, and we use this in chemistry when we talk about the average atomic mass, for instance, of different elements. It's exactly the same. So what this equation says is the density of your cylinder is equal to the fraction that's copper times the density of pure copper. That number is actually the density of pure copper. Plus, Y here represents the fraction of the brass that is pure zinc. And this is the density of pure zinc. Now, that's one equation to unknown, right? So we need another equation. Well, that's pretty easy, because there are only 2 components, copper and zinc. We know that their fractions have to add up to be equal to 1. That's just like saying the percents have to add up to 100, right? If there's 2 things, the percent of A plus the percent of B has to equal to 100. The fractions have to add up to 1. So we can write that down like this: x plus y is equal to 1. So that's our second equation. We can use substitution to solve the top equation by rearranging this, solving for y. Y is equal to 1 minus x. We substitute 1 minus x for y, and we get this. This is something we can work with. One equation, one unknown, x. But in order to solve this for x, we need to know the density of the cylinder. That's where your measurements come in. So remember, density is mass over volume. Mass is easy. We're just going to weigh this on a balance. Now the volume, because this is a regular geometrically shaped object, we can make a couple of simple measurements and calculate the volume. The formula for a volume of a cylinder is pi r squared h, where r is the radius, h is the height or the length. And the radius is the diameter over 2. So what we're going to do, guys, to make those measurements is we're going to use a set of calipers. It'll look like this, and this will allow us to measure the height or the length of the cylinder this way. And you'll see how to use these things in a few minutes. And the diameter, just like this, divide that by 2, and that's our radius. And now we know everything that we need to get the density. Knowing the density, we can solve this equation for x. Remember, x is the fraction that is copper. Multiply that fraction times 100, and that gives you the percent of your brass that's copper. And to get the percent that's zinc, you can just take 100 minus the percent that's copper, and you have the percent that's zinc. And that's really all there is to this lab. So why don't we go over there and get started doing the experiment. All right, guys, so this is how to use the calipers to measure the cylinder. So first thing is, if you look at this caliper, there's 2 scales. On the top is the inch scale, and the bottom is well, it says millimeters, but we're going to read it in centimeters. We use the bottom scale, we read it in centimeters. Now when we look at this, we see some numbers, 10, 20, 30. 10 millimeters is 1 centimeter, so that's 1 centimeter at the 10, 2 centimeters at the 20, 3 centimeters at the 30, and so on. The next thing is each of these small marks is 1/10 of a centimeter apart. So 1.1, 1.2, and so on. Now, so that gets us 1/10 of a centimeter. But we can go farther than that because on these vernier calipers, on the bottom, this jaw that it slides, the way we read it is first we find where the 0 lines up. So with this reading, the 0 lines up between the 2.1 and the 2.2, somewhere in there. So it's going to be 2.1 something centimeters. The next thing we do is to get the next place out is we find which of these lines on the bottom lines up most closely with the line on top. And in this case, it looks to me like probably the 4 and the bottom scale probably lines up most closely. It's kind of a judgment call there, but let's call it that one. So that means that we know that this reading is 2.1, that's from the top scale, and then 4 from the bottom scale. So it's 3 places past the decimal, 2.14 centimeters. So when you read these calipers in centimeters, the number always ends in either a 0 or a 5. And it's going to be 3 places past the decimal. That's how you use the calipers. All right, guys, so this is the first part of the density experiment, and all we're going to do is measure the mass of 10 milliliters of DI water 5 times. So a couple things. First time using the balance, so I'm going to explain how to use it. We're going to measure the water in a 30 milliliter beaker. Now, we don't care how much this beaker weighs. It's not going to be involved in our calculations. So what we do is we use what's called the tare, T-A-R-E, function on the balance. And this basically will subtract out the mass of the empty beaker for us. Really nice. So we open up the balance, place the beaker on the pan, close the doors, and it says some number, we don't care. Press the T for tare. Now that balance reads 0.000 grams. It's subtracting out the mass of the beaker for us. Another thing about these balances, they always give you 3 places past the decimal, so it's real important that you record all those. So now we're going to measure 10 milliliters of water into that and then weigh it on the balance. One thing is we never ever add anything directly onto the balance. So we're going to take this out. Now the display says some negative number, we don't care. When we put it back on, it'll still have subtracted out the mass of the empty beaker. So I have some deionized water that I poured into a beaker here. I'm going to use this volumetric pipette with a pipette bulb. First time using the volumetric pipette, so I'll demonstrate it for you. So this is the top, this is the bottom. There's a line on each volumetric pipette. somewhere in the top here, in the neck. It's going to be different places for different pipettes because they're all calibrated. What we're going to do is we're going to use this bulb to pull the water up above this line somewhere, and then we're going to use our finger to make the meniscus that's at the top of that column of water just touch the top of that line. That'll be 10 milliliters, just like this. So I put the pipette in the water, lift it a little bit off the bottom, squeeze the bulb, keep it squeezed. Now inside of this bulb, it's an inverted cone. It's not gonna like snap onto here. Just have to kind of move it around and see where it fits best. My left forefinger I'm gonna have right here. Make sure it's dry. Make sure there's no water on anything in here. Then I'm gonna start releasing the bulb. Pulls the water up. Remember, I'm gonna pull it up past this mark. This mark's right here. Once I get it up past the mark, I take the bulb off real quickly, put my finger over top, and that keeps it from falling out. Now there's a meniscus right here. I need the bottom of that meniscus just touching the top of this line. So I'm going to release a little bit of pressure with my finger and twist the pipette until the meniscus just touches the top of that line like that. Put the pressure back on, and then I hold it over the beaker, take my finger off. We want to make sure that we let gravity pull the water out of the pipette. What you don't want to do is you don't want to push it out with the bulb. Here's why. After it finishes coming out, you touch it to the side, and there's going to be a little bit left in the tip. It's supposed to be there. I just transferred 10.00 milliliters of DI water to that beaker. If you push that extra little bit out, it's more than 10 mils, and you don't know how much. So I place this back on the balance. Close the doors, read that number, 3 past the decimal. That's the mass of my first 10 milliliters of water. It should be just under 10 grams. Now I'm going to repeat that 4 more times. After each measurement, I take that water, I don't throw it out yet, I pour it into here. It's any beaker, your 150 beaker. Dry this out, and then do the same process 4 more times. At the end of the 5 measurements, you should have about 50 milliliters of water in your beaker. The last thing you need to do is take a digital thermometer and measure the temperature. Because you need to know the temperature of your water, that's going to determine what the true value for the density is. So with a digital thermometer, real easy to read, there's 2 switches on the thermometer. One is the on-off switch, so we just turn that on. The next goes back and forth between degrees Celsius and Fahrenheit. We always read it in degrees Celsius. It's on there. And the last thing about this, well, a couple more things. First is this one gives us 1 place past the decimal, so we always record 1 place past the decimal. Even if it was right at 10, it would say 10.0. We have to record the 10.0 degrees Celsius. The next thing is when we measure anything with this, we don't want to touch down here on the metal part because that can pick up the temperature and alter the reading. So we hold it in the plastic part, put it in the water, try not to touch the bottom if we can help it, let it equilibrate, write that number down. That's all there is for the first part. For the second part of the experiment, it's our brass cylinder. Remember, all we need is the mass and the volume. We're going to calculate the volume, so we're going to measure the length and the diameter rather with the calipers. The mass is easy. We just measure it on the balance. Now, here we can put this directly on the pan, guys. So we want to make sure that the balance says 0 before we put this on. Nothing on the pan. It does. Open up the door, place it on the pan, close the door. Read that number, 3 places past the decimal. Units are grams, little g for grams, and that's the mass. To get the height or the length, we measure it this way. So we just take our calipers, open them up, place them about there in the jaws. We don't want to put them down all the way here. It's a little bit off there. We can actually lock the calipers like this, take the cylinder out, and now we can record our measurement. Then the last part is we measure the diameter, which is going to give us the radius, just like this. So we can lock it in, take it out, take that reading, just like I showed you earlier. And that's everything for the first experiment. You're all done.